Welcome to our series on essential concepts and terminology in transportation planning. In this lecture, we will explore the fundamental concept of the trip generation. Trip generation is the first stage of the transportation demand forecasting process, where we analyze travel frequency, specifically how many trips a traveler will make on an average day. Transportation is not an end in itself, but it is a means to achieve a specific activities. For this reason, transportation demand is referred to as derived demand. Since trips originate from activities, forecasting trip generation requires a model that can logically consistently explain the causal relationship between travel behavior and the underlying activity system. Before discussing trip generation, it is necessary to clarify the basic analytical units: trip, trip chain, and tour. A trip refers to a one-way movement from an origin to a destination to perform a specific activity. A trip chain refers to a sequence of consecutive trips. Among these, a closed-form trip chain that starts from the initial origin, passes through various activities, and eventually returns to the starting point is specifically called a tour. The concepts of trips and tours are fundamental to understanding the two major approaches to travel demand modeling. That is, travel demand forecasting is broadly divided into trip-based models and activity-based models according to how they consider the mutual influences between trips. Trip-based models assume that decisions for each individual trip are made independently. In contrast, activity-based models treat the entire daily tour from leaving home to returning home as the unit of analysis and assume that prior activities influence subsequent travel behavior, including activity participation and travel choices. Activity-based models explicitly represent the detailed activity systems of individual travelers and are therefore theoretically superior. However, they involve complex analytical processes and require extensive, detailed data, making their practical application challenging. In particular, destination choice models within activity-based frameworks must account for linkages between preceding and subsequent activities while simultaneously considering a large number of traffic analysis zones as alternatives, significantly increasing computational and practical difficulty. Considering analytical efficiency, we will focus on the trip-based model, which is universally utilized in professional practice. The basic unit of trip generation in trip-based models is the linked trip. A linked trip is a concept that views the entire journey from origin to activity destination as a single trip. For instance, even if multiple transportation modes are used to reach the activity site, the entire journey is counted as one trip. This contrasts with the concept of an unlinked trip, where each leg of travel on a different mode is treated as a separate trip. Trip generation constitutes the first step of the conventional four-step travel demand modeling framework. In this step, we analyze and forecast trip productions, the trips generated from each traffic zone, and trip attractions, the trips drawn into each zone. The productions and attractions estimated in this step serve as the essential input data for the subsequent stage of analysis, the trip distribution model. In general, since the daily activity frequency of an individual remains within a certain limit, the total volume of daily trip generation, being a derived demand of such activities, is also bounded. Furthermore, trip generation volumes predicted in association with travelers' socioeconomic characteristics tend to be relatively accurate. In particular, when viewed from the perspective of aggregation at the traffic analysis zone level, the prediction of trip generation becomes more stable and reliable due to the statistical properties implied by the central limit theorem. Consequently, the total system-wide trip generation predicted at this stage acts as a reliable control total, providing a macroscopic benchmark for the subsequent analytical stages: trip distribution, mode choice, and traffic assignment. In general, trip generation analysis distinguishes between urban travel and interregional travel because their underlying travel patterns are fundamentally different. Urban travel patterns are characterized by a high proportion of regular and repetitive trips. These trips typically exhibit a daily cycle in which travelers depart from home and return home within the same day, resulting in a stable and predictable pattern. This high regularity and stability provides a significant advantage in ensuring forecasting accuracy during the modeling process. In contrast, intercity transportation patterns are characterized by irregular and intermittent occurrences. The spatio-temporal scope is much broader, and trips do not necessarily repeat on a daily basis. This irregularity makes accurate travel demand forecasting more challenging. Furthermore, because intercity transportation covers vast geographical areas, the high cost of data collection makes it difficult to obtain detailed base data. Consequently, there is a tendency to focus more on macroscopic and aggregate movement patterns rather than microscopic individual behaviors. Consequently, direct demand models, which simultaneously account for trip generation, distribution, and sometimes even mode choice, are frequently applied to intercity travel analysis. Here, we will focus on urban transportation and the conventional four-step demand model, which offer relatively higher levels of precision. Urban transportation typically exhibits a cyclical pattern where travelers depart from home in the morning and return in the evening. Therefore, analysis is conducted by distinguishing between trips that originate or terminate at home and those that do not. These are formally classified as home-based trips and non-home-based trips. A home-based trip is defined as a trip for which either the origin or the destination is the traveler's home. In contrast, a non-home-based trip refers to cases where both the trip origin and destination are not home, and these mainly occur as intermediate stopover activities within a trip chain. The rationale behind this distinction lies in the fundamental differences in trip-making behavior and the determinants of trip generation. The logic of this distinction is to improve accuracy by applying appropriate models separately to each category. Trip generation for home-based travel is typically explained by household characteristics such as household size, income, and vehicle ownership. In contrast, trip generation for non-home-based travel is more appropriately modeled using attributes of activity locations, such as employment counts and the floor area of commercial facilities. This clear distinction allows for a more precise reflection of the underlying causal factors of travel. Home-based and non-home-based trips are further subdivided by trip purpose for detailed analysis. This is because the regularity, frequency, and the specific factors influencing trip generation, as well as the magnitude of their impact, vary significantly across different purposes. Home-based trips are generally categorized into home-based work trips, home-based school trips, home-based shopping trips, home-based social and recreational, and home-based other trips. In large metropolitan areas, or when a more detailed analysis is required, trip purposes may be further subdivided into finer categories. These purpose-specific trips can also be grouped into mandatory trips and discretionary trips based on their regularity. Mandatory trips, such as commute and school trips, are trips that must participate in activities regularly on a daily basis. Consequently, these trips generally exhibit relatively high forecasting accuracy. Discretionary trips, such as shopping or social and recreational trips, occur intermittently based on individual choice. The explanatory variables used for forecasting these trips, as well as their sensitivity to those variables, differ from those associated with mandatory trips. Non-home-based trips have relatively lower generation volumes compared to home-based trips, and understanding the land-use relationship between the two traffic analysis zones is important. Non-home-based trips are commonly divided into non-home-based work trips, such as work-related travel between workplaces and business trips, and non-home-based other trips, such as shopping, dining, and personal business unrelated to work. Because non-home-based trips arise from diverse motivations and occur as intermediate activities in irregular trip chains, their forecast accuracy is somewhat lower compared to home-based trips. The concepts of origin and destination are intuitive because they represent the physical direction of travel. However, they are inefficient for travel demand forecasting and modeling. The fundamental limitation of the OD concept is that the underlying causes of trip making are unrelated to travel direction. The true sources of travel are the travelers, who is the activity agent, and the land use that facilitates those activities. For example, a trip arriving home after shopping and a trip arriving at work are both classified as arrival destinations trips. Nevertheless, the factors that generate these trips are fundamentally different. Since trips starting from or ending at home are generated by the household members, household attributes are what influence trip generation. The concept of measuring trip volumes associated with the residents is termed production. Conversely, measuring trip volumes associated with the activity site that draws trips, such as a workplace or commercial facility, is termed attraction. Thus, land use characteristics are the primary determinants of attraction. If the origin-destination concept is applied directly, trips classified under the same arrival category but associated with different activity purposes would require separate trip generation models. This results in unnecessary complexity and inefficiency. In contrast, the concepts of production and attraction focus on causal relationships with trip generation factors while predicting origin-destination trips together at once, making it simple and efficient. In other words, by redefining trip ends into productions and attractions based on activity purposes and causes, model construction is simplified and causal relationships become clearer, leading to higher forecasting accuracy and analytical efficiency. More precisely, for home-based trips, the home end is defined as the production and the opposite end is the attraction, regardless of the physical direction of travel. For non-home-based trips, the standard general definition for practical consistency and analytical efficiency is to designate the origin as the production and the destination as the attraction. A simple example is used to illustrate how OD and PA matrices are constructed. Case 1 illustrates a simple round-trip pattern where travelers A and B commute from their homes in Zone 1 to their workplace in Zone 2 and return. Since all these are home-based trips, Zone 1, the residential location, is the production zone. Therefore, regardless of the travel direction, all 4 trips are counted as productions at Zone 1. Consequently, Zone 2, the workplace location, becomes the attraction zone, and all 4 trips are counted as attractions at Zone 2. In the OD matrix, which accounts for directionality, the trip volume from Zone 1 to Zone 2 is 2, and the volume from Zone 2 to Zone 1 is also 2. For these simple round-trip patterns, the OD matrix appears perfectly symmetrical across the diagonal. However, it is important to note that the PA matrix is fundamentally based on behavioral foundations, such as household attributes for productions and activity site attributes for attractions. Due to this behavioral basis, the PA matrix is inherently non-symmetrical, unlike a simple OD trip structure. Moving on to Case 2, we introduce a more complex situation involving 2 travelers with trip chains, which results in non-home-based trips between Zone 2 and Zone 3. For non-home-based trips, we define the origin zone as the production and the destination zone as the attraction. This is a crucial distinction. Unlike home-based trips, where production and attraction are based on household and activity characteristics, for non-home-based trips, the production and attraction points are conventionally set to align with the actual origin and destination of the trip. Consequently, in this case, the directional flow of production to attraction is identical to the origin to destination path. Finally, in Case 3, we observe 3 travelers with even more complex trip patterns. Comparing the OD matrices across these cases, we can observe that Case 2 shows a symmetrical pattern, while Case 3 does not. This is because Case 2 follows a simple round-trip structure, whereas Case 3 involves more complex travel patterns. Regardless of individual travel identities, an OD matrix maintains symmetry only when the aggregate travel pattern follows a simple round-trip structure. In reality, because trip chains are common, OD matrices used in practice are mostly asymmetrical. This asymmetry is even more pronounced when analyzing travel patterns by specific time periods, such as peak and off-peak hours, due to directional imbalances. Therefore, when an OD matrix appears symmetric, the analyst must understand that the data was likely constructed under the assumption that aggregate travel follows a simple round-trip pattern. Analysts should be aware of this underlying assumption in mind when utilizing OD matrices for modeling and evaluation. As in the trip generation stage, the trip distribution stage is also analyzed using the concepts of trip production and trip attraction. However, the subsequent stages, mode choice and traffic assignment, involve alternatives and network conditions that vary significantly based on the direction of travel. Therefore, it is essential to convert the directionless PA matrix into a directional OD matrix. There are two primary methods for converting PA volumes into OD volumes. One method is to simply split the PA volume between production zone A and attraction zone B in half. 50% is allocated as the OD volume from A to B, and the remaining 50% is allocated from B to A. When this method is applied, the resulting OD matrix becomes perfectly symmetric about the diagonal. This implies a rigid OD travel pattern assumption, where all travel is considered a simple round trip. The method is computationally straightforward and does not require additional survey data, making it easy to apply in practice. However, it is difficult to apply to time-of-day analysis because trips during specific periods often represent only a one-way leg of a complex activity chain rather than a complete round trip. If an analyst adopts a perfectly symmetric OD matrix, it must be clearly recognized that this reflects an underlying assumption of aggregate round-trip patterns, and the resulting outputs must be interpreted with professional caution, acknowledging the limitations imposed by such assumptions. The other method is to convert PA trip volumes to OD trip volumes using conversion factors based on actual trip survey data. The conversion factor represents the proportion of OD trips where the production zone is the origin and the attraction zone is the destination within the total PA volume for a specific pair. The formula for this conversion is shown on the screen. Let's take the conversion formula between Zone 1 and Zone 3 to understand how we convert PA trips into OD trips. Specifically, let's look at the equation for OD13. To calculate OD13, the first term, lambda 13 times PA 13, represents the trips produced in Zone 1 and attracted to Zone 3 that are actually traveling from Zone 1 to Zone 3. Here, lambda 13 is the conversion factor that isolates this specific directional flow. The second term, 1 minus lambda 31 times PA 31, represents the trips produced in Zone 3 and attracted to Zone 1, but moving in the return direction, that is, traveling from Zone 1 back towards Zone 3. This calculation shows that the total OD13 trip volume is the sum of the outbound portion of PA13 and the inbound portion of PA31 trips, both of which are headed from Zone 1 towards Zone 3. The calculation for the reverse flow, OD31, follows the exact same logic. When this method is used, asymmetric OD patterns due to trip chaining can be properly estimated, as shown in the example. However, the challenge lies in the requirement for detailed sample survey data to determine the conversion factor for each zone pair. Production focuses on the behavioral characteristics of individual households. Accordingly, data obtained from household travel surveys can be analyzed at different levels of aggregation, such as the individual, household, or traffic analysis zone (TAZ) level, depending on analytical needs. However, in the case of attraction, since it is influenced by the land use conditions and activity systems of specific TAZs, physical indicators such as facility floor area and number of employees become the influencing factors rather than individualized behavior. Consequently, attraction, which is largely determined by land use intensity and diversity, is typically analyzed at the TAZ level. Both production and attraction are analyzed by trip purpose, examining their relationships with various explanatory variables separately. Production models generally include household income, vehicle ownership, household composition, and employment status as explanatory variables. Because production models are built using detailed household-level survey data and explicitly consider behavioral causality, they generally exhibit relatively high explanatory power. By contrast, attraction models typically include explanatory variables such as employment by sector, commercial and industrial floor space, and enrollment capacity of educational institutions. Because land use types and activity patterns are highly diverse and subject to significant variability, attraction models tend to exhibit lower explanatory power and predictive accuracy relative to production models. When analyzing the relationships between productions or attractions and their explanatory variables, it is important to determine whether the relationships are linear or nonlinear and to select appropriate functional forms for use in forecasting. The selection of an appropriate trip generation model depends on the purpose of the analysis, the characteristics of the study area, and the availability and quality of base data. The most commonly used models are the growth factor method, category analysis, also known as the cross-classification method, and regression analysis models. The growth factor method is the simplest forecasting approach, where future trip volumes are derived by applying historical trends and projected growth rates of indicators to current observed volumes. This method does not require complex base data and is straightforward to apply. However, because it does not account for differences in characteristics or structural changes among individual TAZs, its predictive accuracy is relatively low. Therefore, it is primarily used for estimating trips entering or leaving the study area, where detailed base data are often limited. Category analysis categorizes households by combining key variables such as income and vehicle ownership and applies average trip generation rates to each category. Rather than explicitly modeling complex correlations among variables, this approach relies directly on empirical data stratified by socioeconomic characteristics. Trip generation regression models have the most solid statistical foundation and are the most widely used models in practice. These models mathematically derive the relationships between productions or attractions and their explanatory variables through multivariate statistical analysis. This model's analytical approach varies depending on the aggregation level of input data. Currently, the most common practice is to estimate models using disaggregate household-level data, directly utilizing individual household survey records. For more refined and behaviorally sensitive forecasts, models may also be calibrated using disaggregate individual data that includes detailed personal activity characteristics. Category analysis is a method for forecasting total trip volumes by classifying households into categories based on combinations of variables that influence trip generation, such as household income and vehicle ownership, and applying the average trip generation rate for each specific category. The fundamental assumption of category analysis is behavioral stability, which means that the trip generation patterns of a specific household category remain relatively stable over time. Furthermore, category analysis applies the same category-specific trip generation rates uniformly across all TAZs, and therefore is not directly influenced by the spatial structure of the TAZ system. A key feature of this method is that it is a non-parametric approach, meaning it is free from the constraints of predefined mathematical functional forms. Unlike regression analysis, which requires the estimation of coefficients for a specific equation, category analysis does not assume a fixed relationship like linearity. Consequently, when the observed relationship between explanatory variables and trip volumes is nonlinear or exhibits irregular patterns, category analysis can reflect those forms in the model as is. However, improving predictive accuracy generally requires a finer segmentation of categories. This introduces the practical challenge of accurately forecasting and inputting the future number of households for every single category across all traffic zones. Moreover, if categories are subdivided too finely, the number of observations in each cell may become insufficient, reducing the statistical reliability of the average trip rates. Therefore, careful category design and an appropriate balance between detail and sample size are essential. Theoretically, category analysis can be applied to both production and attraction. However, in practice, it is mainly used for production analysis. Every trip has both an origin and a destination, and correspondingly, production and attraction exist simultaneously at both ends of the trip. Therefore, logically, the system-wide sum of total productions must equal the total attractions within the entire study area. However, in actual analysis, since production and attraction are estimated using different variables and independent models, their predicted totals rarely match. Consequently, before moving from the trip generation stage to the trip distribution analysis stage, a balancing process must be performed to equate the totals on both sides. Prior to balancing, the analyst must determine which side, production or attraction, is more reliable and should serve as the control total. In most cases, production serves as the control total. This is because the socio-economic variables influencing production, such as household income and vehicle ownership, tend to be relatively stable, and the estimation error in average trips per household is generally smaller than that of attraction models. Accordingly, in most cases, attractions for each zone are adjusted to match the total productions. Conversely, in some cases, total attractions are more reliable and thus serve as the control total. A representative example is home-based school trips. Data on student enrollment and facility capacity are typically well documented and readily available from public sources. But estimating how many students from each individual household attend a specific school is relatively uncertain. In cases like this, where attraction side data are more certain, productions are adjusted based on the total attractions. The balancing of productions and attractions is not merely a numerical adjustment to equalize totals. Rather, it is a process for ensuring analytical consistency based on the most reliable data available. In the next lecture of our series on essential concepts and terminology in transportation planning, we will focus on the topic of the trip generation regression model. Thank you for watching. I would love to hear your thoughts or comments on today's lecture. If this explanation was helpful, please like and subscribe to support this series.